Hi, I'm Diana and I'm going to present our work on multimodal pre-training audiovisual math autoencoders. We have seen that the current trend in computer vision is to train larger models on larger datasets. However, obtaining large annotating video datasets is not always possible. To overcome the lack of annotating video datasets, researchers use pre-training image models to initialize video models. We believe that the math autoencoder framework can be an alternative to pre-trained video models. In this work, we focus on video and sound because they are naturally present in video. We observe that the previous works ignore the additional auditory information which is already present in video datasets. In this work, we study if you can leverage the multiple modalities to learn stronger representation that can be used for both multimodal and unimodal downstream tasks. We briefly recap the mask autoencoders framework. The first step is to tokenize the input, then we remove a predefined percentage of the tokens. The unmasked tokens are encoded. After that, learnable masked tokens are added to the sequence of tokens. And finally, we reconstruct the image by decoding the token. Our framework is simple and effective. We first learn the correlation between modalities in the encoder during pre-training. After pre-training, we remove the decoder and fine-tune the encoder on different downstream tasks. We present different alternatives for combining audio and video information. We use this alternative for either the encoder or the decoder of MAE. The first one is early fusion, where we concatenate the tokens and pass them to the transformer. The second choice is the separate strategy, where you have different transformers for each modality. The third choice is the share strategy, where you share the transformers' weights between modalities. The last choice is unit fusion, where we use a few transformer layers to encode each modality separately. Then we concatenate the resulting tokens and feed them to a joint transformer. In this work, we propose two reconstruction objectives. The first one is a simple joint reconstruction, where we encode and reconstruct both modalities using equal loss weights. The second reconstruction objective is the modality in painting, where we decode one modality using the encoded representation of the other modality. For this to be possible, we need to encode the modalities jointly. Otherwise, the visible tokens will not contain information about the decoded modality. The experiments we perform have two stages, pre-training and fine-tuning. We also perform experiments on three downstream modalities, and we perform experiments on three datasets. We apply the architecture strategy while using the joint reconstruction loss. We can observe that separate and mid-fusion encoder strategies perform the best, especially in audio-visual fine-tuning. The reason behind that can be that the encoder is able to learn specific weights for each modality. However, for the decoder, we observe that having a shared strategy works the best. After that, we switch the encoder strategy to separate and the decoder strategy to shared, and apply the reconstruction objective. We notice that a simple joint reconstruction obtained better results, while the modality in painting objective is harder to train. We also demonstrate the transferability of the features learned with our method by fine-tuning on different datasets. Our method does not suffer from overfitting, being able to scale up the backbone without losing performance, unlike supervised pre-trained baselines. We also demonstrate that audiovisual MAE is better than pre-training to separate models. Full details about these experiments and other ablations are in our paper. We compare our pre-training strategy with the state-of-the-art. We would like to emphasize that in this work we only propose a self-supervised multimodal pre-training strategy, while other methods use supervised pre-training on multiple datasets. Our model is simple, having the VIT model as encoder for unimodal tasks and the MBT model for multimodal tasks. We also notice that other methods use modality-specific architectures. However, we can still achieve state-of-the-art results with this simple set. On the VGG sound dataset, we obtain the best results on audio-only and audio-visual downstream tasks. On audio set, we obtain large improvements on audio-only and audio-visual tasks due to the usage of audio information in the pre-training stage. While on Epic Kitchens, we obtain large improvements, especially on the word classes. In conclusion, in this work, we leverage multiple modalities present in video for pre-training. We demonstrate that multimodal MAE is effective on both unimodal and multimodal downstream tasks. Also, multimodal MAE decreases the pre-training time and increases performance on unimodal and multimodal tasks, as we show in the paper. If you find our work interesting, check out our paper and code online. Thank you for watching.